Alrighty boys, for our experiment we decided to figure out the air resistance on a leaf. And we did that by dropping the leaf from a known distance of 1.4 meters, as drawn in the diagram over there. The mass we calculated to be 0.29423 grams. And the surface area was also measured using an app provided to be 0.001 meters squared. And the time it took to fall was recorded to be 1 second. And using that, we're going to calculate the acceleration of the leaf, which could then be used with the FNet diagram to figure out the frictional force applied to it, which will then finally be used using the surface area to find the amount of frictional force applied per meter squared to a flat surface in an environment just like this. Alright, so now we're going to do the kinematic equations. So the equation we're going to use here is
delta V, which is difference in distance, which in this case 1.4 meters, equals to initial velocity times t plus half the acceleration times t squared.
Alright, so the unknowns, the knowns in this question are the delta D, which is 1.41 meters. Alright, and we know the initial velocity to be 0 meters per second. You know why? Because we dropped it from rest, alright? And the time it took to drop was 1 second. Makes the calculations easy. So what we're solving for is acceleration. Question mark, because we don't know it yet. Let's plug this guy in.
Right, so that, for the distance, it's 1.4 meters, like we said before. Initial velocity 0 meters per second, times the time, which is 1 second, plus half the acceleration, which is 1.4, times the time, 1 second squared. Now moving forward, then 1.41 meters equals half acceleration, 1 second squared. 1.41 meters times 2 equals acceleration times 1 second squared. And 1.41 meters times 2.
I'm not even using a calculator for this one. 2.82 meters per second squared equals A. So now we've got the acceleration. We can put that into the constants table now, right? We can use that to calculate the net force acting on the leaf since it's accelerating downward, alright? So force equals mass times acceleration, as we all know, alright? So Fnet, just plug it in, you see there, so Fnet now, equals the mass, which
2.9243 times 10 to the power -4 kilograms is
SI units. And then acceleration, which is
2.82 meters per second squared. Alright? Now,
this is, give me 1 second, alright boys and girls?
alright, we got one number in. That's the second number in already. We got
8.247 times 10 to the power -4 newtons. So that's the net force acting on this leaf.
So now that Sanjeevan has found the acceleration on the leaf and the net force acting on the leaf, we can show this with the free body diagram of the leaf. And the two forces acting on the leaf is the force of gravity down, and then also we have the force of the air resistance. But the net force is 8.247 times 10 to the -4 newtons, which is down. We're calling that direction positive. So the sum of these two forces will equal our net force. So we can write down a net force statement. And then plugging in these numbers, we can solve for the actual air resistance on the leaf. So we have our net force is equal to mass times acceleration. In this case, it's not that acceleration that we found. Times 9.8 meters per second squared. And rearranging this equation, we can find that the force of the air on the leaf is equal to 2.0537 times 10 to the -3 newtons. Okay, now that we've found the force of the air resistance on the leaf, we can find this per meter squared using the area of our leaf that we found to be 0.001 meters squared. So this force divided by the surface area of the leaf gives us a force of 2.0537 newtons per meter squared.